basically I want to just finish up a couple of things talking about these basic concepts of the central limit theorem and the empirical rule, and then we're going to start kind of working our way through different statistical types. The first set of statistics that you can do is statistics on categorical data, either nominal data or ordinal data, and then we will get to interval and ratio scale data. So what we've been doing up to this point is we've been talking about parametric statistics. And parametric statistics are just the kind of statistics that rely upon the estimation of a particular parameter. And in this case, the parameter that we've been relying on is the sample mean. And the problem with the sample mean is that sometimes the sample mean doesn't always reflect the population mean that we're trying to estimate. And one of the most common ways in which this happens is when you have data that are skewed, where the data are not normally distributed, but the data have a tail, either a tail that goes out to the right, which is called positive skew, or a tail that goes out to the left that has negative skew. And what happens when this happens is the mode is here. The median is going to be relatively close to the mode. Who can tell me what the median is? Yeah.
50th percentile of the middle value of the data.
Okay, it's the middle value of the data, so it'll be a little below or a little above the median, depending on how skewed this is. So the median could be here, the median could be there, and it'll all depend. But the median is going to be much closer to the mode, and the mean is going to be pulled out this direction because of the weight of these relatively few but relatively large values that are in this distribution. And so the mean is skewed away in a positive direction from the median and the mode. And so skew is really common in biological data. We see it a lot. We actually see this form of skew, but you also see this form of skew in other fields as well. There is a data set of people's response times on a test, and they're taking a test on a computer, and the researchers just looked at how long it took them to respond to questions. And a lot of the responses are relatively quick, but then there's this tail of longer responses that basically have to do with the person keying something in incorrectly, having to go back and correct it, et cetera, et cetera. And so skewed data is relatively common. So these are just some codes for different ways in which you can calculate some summary statistics on a given sample. But when you're doing parametric statistics, there are a set of assumptions that have to be met in order for doing statistics on numbers. And two of these are tested using these two functions in R. I'm not going to show them to you right now because we don't really need them yet, but I want to talk about assumptions in general of parametric tests. The first assumption, and it's an assumption that you can make because you generally set up your sampling scheme to account for this, and this assumption is that the data are independent from one another. Going back to the example of GPA at colleges and universities, if we were interested in knowing what the average GPA is of students, we could go to William Jewell College and we could take a random sampling of students. And because that sample is random, we would be able to assume that these things are probably independent of one another, but it would all depend on how we went about gathering those data. If we accidentally got two siblings who happen to both be attending William Jewell College, well, clearly those two data points are not independent of one another because not only do you share genetics, but you also share a common educational environment, you share a common parental home environment, et cetera, lots of ways in which those two things are not independent. So first thing we want to do is we want to ask everybody is, are you a sibling with anybody on William Jewell College? And if so, who is your sibling? So we don't include them in the sample now that we have measured you. Another thing that might happen, and this is really common with undergraduate psychology projects, people will set up a table in the union and they will catch people going into the cafeteria and they will say, hey, do you have a couple minutes to help me with my research? And they'll give them a survey or give them a little test or something like this. But if students are walking to the cafeteria in groups, so for example, let's say a bunch of swimmers just got out of swim practice, they're coming up to get in line at the end of the mealtime, because I know swimmers have to swim like 3 times a day, it seems. And so you have a group of swimmers coming in, they walk past the table, and then all of a sudden you have added to your data set data from 5 swimmers. Nothing that says that swimmers have a different GPA than the rest of the population as a whole, but because you sampled in such a way that you got these 5 people who all share this one thing in common, might make those data not really independent. What you should select is like, okay, there are 5 of you, we'll take 1 of you, the rest of you go eat, et cetera, et cetera. So independence is generally accomplished in the way you collect your data, but it is an assumption. The second of these is that the distribution of sample means is reasonably expected to be normal. And we actually have a numerical test where we can test for this. It's called the Shapiro test. And at the end of this segment that we're about to start on categorical data, we'll actually show you how to do a Shapiro's test. Sorry. There should be, this is actually number 3. The second assumption is that your data were collected randomly. Sorry, I kind of lumped that into the first one when I was talking about it, but it is a separate assumption. And then the fourth assumption is that the variances are equal or at least similar to one another. You will usually see these in a statistics book written in this order. The first 2 of these, you take care of yourself as a researcher in terms of the way you collect your data. So these things are generally true. We'll discuss some situations where they're not true, and they're not true for good reasons. We have different kinds of statistical tests for testing hypotheses when the data are not independent. But these other 2, we can actually test them using a Shapiro's test and using a homogeneity of variances test. But they're listed in this order in spite of the fact that this one is actually the one that is most important. We can assume that this is true if we have a sample size that is sufficiently large. We can assume that the sample mean distribution is going to be normal because we can always fall back on invoking the central limit theorem. So it's really this one that kind of bites us in the butt periodically. And let me explain to you why that's the case. If we have a population of observations, whether it's normal or not, it doesn't really matter. We go into this population, we select a set of observations from this population, and from that, we calculate a mean. Now, once we have that mean, we can calculate the variance, the standard deviation, the standard error, and we can construct a 95% confidence interval around that mean, what are the couple of ways that we can interpret this 95% confidence interval? Somebody other than you. Sorry, Karis, you're always answering. We've been through a couple of ways in which we can interpret this. What are they? This is a fundamental. You need to know this. What does a 95% confidence interval mean? How can you interpret that? Yeah. So there's a 95% chance that there's a 95% probability that the population mean is somewhere in there. So that's one way of interpreting this, is that it's an estimate. It's an estimate of the population mean with some error thrown in. So depending on how big our sample is, that range has to be big if we have very little data, or it gets smaller if we have a lot of data. But somewhere in there should be the population mean. Population might not be in there because we missed it, because of this is always just an estimate. What's another way of interpreting the 95% confidence interval? I would argue a more useful way. Not that the first way is incorrect, it's just a little less useful. If we go back to this population again and sample from it, what does this 95% confidence interval mean? We throw all those observations back in. We go back and sample this population again. We calculate a sample mean from that. How does that sample mean relate to this? If we draw from this population, we should expect this mean to fall somewhere in there. Now, it may be further up, further down, whatever, but 95% of the means we draw from this population should fall within that interval. That's the other way in which this 95% confidence interval is of use to us. Now, let's say that we go to another population, but this population has a really wide distribution of its data. We sample from it randomly, independently, etc., etc. We find the mean of those observations. But what's going to happen when we go to calculate the 95% confidence interval, assuming that the sample size from this population and the sample size from this population are the same? Yeah. The variance is going to be larger, the standard deviation is going to be larger, the standard error is going to be larger. Thus, the confidence interval will be larger. So, we might expect to have a much larger confidence interval. Now, are these two means different or not? Okay, some people are saying no. All right. Raise your hand if you say these two means are different. Raise your hand. Well, I've written it up there. If you were just looking at the means and the confidence intervals, would you conclude that these two means are different, or would you conclude that these two means are not different? How many in favor of different? 1, 2, 3. Raise them high. 1, 2, 3, 4, 5, 6, 7. How many of you would claim that they are not different? 1, 2, 3, 4. Why is there that uncertainty in your minds? Yeah.
Because the first one's in the second confidence interval, the second one's not the first.
So this mean falls within the confidence interval of the purple mean, but the purple mean falls outside of the confidence interval of the blue mean. So are they different or are they not? It's ambiguous. Why is it ambiguous? Yeah. It's ambiguous because one of them falls within the range of the other, but the other doesn't fall within the range of the first. So if you look at it from the perspective of, could blue have come from the population of purple? Yeah, it could have. Could purple have come from the population of blue? Not very likely. So the question when we ask are two means different from one another, we're asking, could we have drawn both of these means from the same population, or is it more likely that we drew these means from two different populations? When we think of the question that way, we ask, could we have drawn blue's mean from purple's population? Sure, it falls within the 95% confidence interval. Could we have drawn purple's mean from blue's population? Probably not, because it lies pretty far outside of the 95% confidence interval of blue. So the root cause here is that we have a narrow variance for the blue population, and we have a wide variance for the purple sample. Whenever you have that, you risk this thing happening. Imagine if purple had the same population mean, but had a similar variance as blue. This 95% confidence interval would now not be nearly as big. Are those two means different? Yeah. Purple is unlikely to have come from blue's population. Blue's mean is unlikely to have come from purple's population. If, on the other hand, we'll put purple's confidence interval back where it was, and now, instead of blue having this nice narrow distribution, blue's distribution was wider. What that does to blue's confidence interval is it makes blue's confidence interval wider. Is purple different from blue? No. Blue could have easily come from purple's population, and purple's mean could have easily come from blue's population. When the variances are similar, it's easier to make decisions because we don't end up with this case where one mean could fall within the confidence interval of another mean, but that mean does not fall within the confidence interval of this one. This is the most important of these assumptions because it reduces ambiguity in the decision-making process. This is very hard to make a decision about. This is dirt easy to make a decision about. They're not different. The other way was dirt easy to make a decision. They are different, but it's because of this inclusion or exclusion of the means. Easier to do that when the variances are similar, because then the standard deviations are similar, the standard errors are similar, and the 95% confidence intervals are going to be similar. So we will, once again, I'll show you how to go about testing this once we're through with this, but I wanted you to have these assumptions before we left this. Questions about that? There's a data, whoa, I just kicked the video. There are, I wanted to call your attention to Data to Viz. There's a website called Data to Viz and it has this flowchart. One of the first things you should do anytime you get some data is just look at it, see what it looks like, see how it's distributed, et cetera, et cetera. And what this website does is it's kind of a flowchart that you can click on. So depending on whether you have numerical data or categorical data, et cetera, It gives you options for how you can visualize the data. It's always a good idea to look at visualizations of your data early on because it will tell you whether you're going to start having problems with analysis. So for example, these are the actual data that are in your homework assignment. The data set with phenotypes of mutant organisms or mutant cells and wild type cells. And you can see that in both of these cases, there might be skew. There's definitely right skew here. There might or might not be skew here. So doing a simple histogram of the data can tell you about what some of your distributional assumptions might or might not be. Do we have to worry about skew in particular? Do we have to worry about skew? Why not? Yeah.
Because we're going to take sample means, and those means will be normally distributed.
Yeah. One of the reasons that we don't have to be terribly worried about skew is because we can always fall back on the central limit theorem. Now, we can only fall back on the central limit theorem if what? What do we need to, especially if we know that we have skew, what should we be doing in terms of our intensity of sampling? Only take a couple of samples, take 10 samples, take 15 samples, take 30 samples. Yeah, we should take as many samples as we can if we know for a fact that we have skew. So we can rely on central limit theorem, but central limit theorem does have its limitations. One of the limitations is that it functions less well when we have smaller sample sizes. So what we want to do when we first get to a set of data is we want to actually just look at the data, see if they're normal. If the data themselves are normal, then the distribution of sample means becomes normal more quickly, so you don't need as big a sample sizes. If the data are not normal, then you need larger sample sizes in order to get the central limit theorem to work. We talked about residuals. Residuals is just the distance between the measure of central tendency that you're using, which in this case is the mean, and the individual data points. Are those residuals distributed normally or not? Are some of those residuals really big, whereas most of those residuals are really small? That has to do with kind of how spread out your data are and whether or not you have outliers. So we have a variety of parametric tests. We will do a number of these. We're going to be doing t-tests. We're going to do paired t-tests. We're going to do ANOVAs. We're going to do correlations and regressions. We're not going to do repeated measures ANOVA, but we'll do a different kind of ANOVA called an analysis of covariance. But for all these things, you need to check certain things about the normality of the data. And once again, as we go through those, I'll explain to you why you want to check residuals rather than something else. When you calculate your graphs, I ask you to make a graph of the data that plots the means and the 95% confidence intervals. I do that because I want you to be doing this type of thinking that is on the board, where you're asking yourself, does one mean, is it included in the 95% confidence interval of another mean? These are those same data. In this case, this is a box plot. Box plots don't calculate the mean and the 95% confidence intervals. They plot the median, the interquartile range, and like the 90th percentile range. And what this is basically showing you is that the red data are probably skewed, the blue data are less skewed, and the reason that the red data are skewed, and the reason that you can see this in a box plot, is because you see that this whisker down here extends further down, or less down, than this whisker extends up, which means that there's more of the data distributed over here than over here in terms of, if we're going to start at 50%, how far up do we have to go to get to 90%? If this is 50%, how far down do we have to go to get 90%, to get to the 10th percentile? And you also see that it shows you a couple of outliers up here at the top. When you look at a box plot, once you learn how to read a box plot, it will show you skew. This is a little skewed, but not very much, because the distance here is not particularly different from the distance here. So box plots are good because they show you kind of what the distribution of the data are. 95% confidence interval plots are useful because they allow you to infer whether or not two means are different from one another. And so looking at your data is always useful. So we have the original data that are here. One way of reducing skew is to take something like a log transform of the data and then testing it again. But once again, we'll talk about that more when we get into actually doing parametric statistics. Any questions about basic parametric statistics as it relates to estimating means, estimating 95% confidence intervals? Okay. There's other stuff in this PowerPoint that we will get to later on. Somebody asked me via email, can I just do this in Excel? It would be so much quicker. Yes, it would be quicker if you did it in Excel, but it would kind of defeat the purpose of the assignment, which is to get you practice with doing the process. I'm a big advocate of forcing you to do the process by hand because that's what cements it in your brain, that you know how the process works. Once I'm confident that you can do that, then we're going to do everything on computer. But until then, I want to do things by hand. So no, don't do it in Excel. If you want to do it in Excel and check your work, that's fine. If you want to do it in R and check your work, that's even better. But in terms of what you turn into me, I want to see that you can actually calculate it by hand. Yeah.
So do you want us to turn in all of our homework on a piece of paper then for this assignment?
Oh yeah. Yeah. I know it's a pain, but once again, it'll give me insight into do you actually know how to do this? Yeah. So I expect sheaves of paper. Although I've spaced it out in the PDF such that you should be able to calculate everything just in the space that's provided there. Yeah.
Take a picture of it and we turn it in.
No, you can just
Hand it in.
print it and hand it in handwritten. Works for me. Yeah.
Do you mind if we mark it up as a file on our iPad?
No, that works too. Yep. You'll see that when you give me your reports and stuff, I will more than likely mark them up on an iPad and send them back to you. Yep. All right. Any other questions? All right. There is a PowerPoint in today's materials on the Moodle site. So I want to back up. Now that we've gotten this idea of measures of central tendency and spread and the central limit theorem and the empirical rule, I want to go back up and think about categorical data. So when we think about data, we can think about data as falling into categories, or we can think of them as actual numbers. And this is the difference between categorical data and numerical data. And what we do is we can analyze categorical data and we can analyze numerical data, but the methods that we use to analyze them are different. And so for categorical data, what we oftentimes will do is we will use chi-square tests. So chi-squares are kind of tricky to people because there are three different kinds of chi-square tests, and the calculations of the chi-square statistic for each of them is exactly the same. But they differ depending on what type of question you're asking, and the kind of question that you're asking determines how you calculate the expected values. So that's where the tricky part comes in, and that's where people usually mess up chi-square tests. So I'm going to explain this to you by doing some examples. So a chi-square test is a goodness of fit test when it's asking does the distribution that I'm looking at, does it match some predetermined distribution? So for example, if you're a geneticist, so in the field of genetics, if you're doing basic genetics, you can make predictions based on what we know about how genes get inherited, about what the expectation is for different types of phenotypes in the next generation. So how many of you can roll your tongue? Okay. So a number of you can roll your tongue, that's a dominant trait. Some of you can't roll your tongue, that's a recessive trait. And if we take a recessive individual that has this genotype and we cross them with a dominant individual that has this genotype, all of their offspring have this genotype. So we have a roller and a non-roller. For those of you who are biologists, you don't have to follow this. I'm just showing you why I'm getting to what I'm getting to. And if we cross these, one allele comes from this parent, one allele comes from this parent, and it produces a population where everybody can roll their tongue. If we then take those offspring and allow them to crossbreed, we get these three genotypes, but 3/4 of the population will be this, and 1/4 of the population will be this. So this is an expectation based on the theory of how genetics works. Now, if we go out to a population of 1,000 individuals that we got from this cross, and we find that 600 of them are rollers, and 400 of them are non-rollers, we can test that to see if it differs from what we expected, because what we expect is, we expect there to be 750 rollers and 250 non-rollers. And so this is a goodness of fit test. We're testing, do our observations comport with what we expected to see? Do the data that we observe fit some theoretical expectation? So that's what we mean when we talk about a goodness of fit. Does one set of data fit another set of data? A chi-square test of homogeneity is just a test to see if the frequencies of the different data are all equal. So for example, if we were in the political season, we might take a political poll. We might find, so in the last presidential election, Trump was running uncontested because he was the president. And so the Democrats went through the primary process. So you had Biden duking it out with Sanders, duking it out with Warren, duking it out with Buttigieg, current Vice President Harris was in the mix early on, et cetera, et cetera. And you might find that there's 30% support for Biden, 20% support for Sanders, 20% support for Warren, et cetera, et cetera. And you would figure out what all these people are who are responding to a political poll. And you might ask, is there a preference expressed in the poll? And so what you would do is 50, 70. Let's say that this was the poll, so that we asked 1,000 people what their preference was. 300 of them chose Biden, 200 chose Sanders, 200 chose Warren, 150 chose Buttigieg, and 150 chose Harris. That's 500, 700, and 1,000. That's 1,000 individuals. There's 1, 2, 3, 4, 5. 1,000 divided by 5 is 200. So this is what we observe. And the expected in this case is just the expectedness of homogeneity. 200 would be the expected for each of these. And we would compare what our observations are to this expected value that is the expected value of homogeneity. And it looks like people might prefer Biden, slightly more so, no preference for Sanders and Warren, and they tend to not prefer Buttigieg and Harris as much. This is testing an observed observation against some standard of equality across all categories. That's what a homogeneity test is. A Chi Square test of independence is when you have, let's see, let's say you have three religious categories. You have Protestants, you have Catholics, and you have people who are either unaffiliated with any mainline denomination or are not religious at all. And you ask them about abortion. Are they in favor or are they not? And what you find, let's say that you have 1,000 individuals once again, you find that Protestants, of these 1,000 individuals, 300 of them, well, no, 100 of them were in favor, 200 of them were not in favor. Among Catholics, 250 of them were in favor, and 50 of them were not in. So, no, that would be just the opposite for Catholics. 250 of them would not be in favor, 50 of them would be in favor. So that's 300 individuals, 600 individuals. And among unaffiliated, it was evenly split. So you have 1,000 individuals, and what this type of test is asking is one's religious belief independent of their support or lack of support for making abortion available to women? And so this is a test of independence because it looks to see how responses vary across denominations in this category versus this category. Are these two variables independent of one another or not? And the way we calculate expected values under this case is much more complicated than in either of these other two cases. So that's actually what we'll cover last. But that's essentially the difference in the types of questions that these three methods are dealing with. Questions about that difference? Okay. Then let us begin. If you have a calculator, you'll probably need it. If you don't have a calculator but you have a smartphone, just pull up the calculator on that. So here we have chi-square test of homogeneity. In this case, the question being asked is being asked by an insurance company. Insurance companies will sell life insurance policies, and you can get life insurance policies for different values. $10,000, $15,000, $20,000, $25,000, or $30,000. And after you arrange with an insurance agent for a life insurance policy, there's usually a little grace period where you can cancel the policy without having to pay any money. And the insurance company is interested in, is there any difference across these categories of different amounts of life insurance in terms of the probability of you canceling that policy before you have to start paying for it? So they looked at policies of different amounts, and they looked at the number of individuals who canceled the policy. And what they want to know is there any difference among these categories? This is a chi-square test of homogeneity because they don't have any theoretical model that they're asking. They're basically asking just, are these proportions different from the proportions you would expect if everybody canceled equally regardless of the coverage of the policy? So the way you would do this is, since we have 250 individuals, we would divide that by 1, 2, 3, 4, 5 categories, and that would basically give us 50 as our expected value. So the expected value would be 50 in each of these cases. Now the way the chi-square test works is the chi-square test is the same, you calculate the statistic the same way for any chi-square that you ever do. So just learn it. It is the observed minus the expected squared divided by the expected and then summed up across however many categories you have. So for this first category, the $10,000 policy, if we wanted to know what the chi-square test was, the chi-square statistic was, we would take 31 minus 50, we would square that value, and we would divide it by 50. Then we would add to that 39 minus 50 squared divided by 50. Add to that 67 minus 50 squared divided by 50 plus 54 minus 50 squared divided by 50 plus 59 minus 50 squared divided by 50. And add that all up, and this is the chi-square statistic. Do that. I'll be back. I need to go blow my nose because I'm wearing a mask. Clear on the math? How's it going, calculation-wise? Done? Nope, still working. Show you what I got, see if we all agree. This is what you guys got. Then we add all those up together, and so the chi-square statistic for this particular test is 17.36. So we generate this chi-square statistic, but then we have to know whether or not this is a large or a small chi-square statistic. So what we do is we go to a chi-square table, and we basically say, how many degrees of freedom do we have? Well, the degrees of freedom is just like degrees of freedom in anything else. In this case, it's the number of categories minus 1. So in this case, we have 5 categories, and so we have 4 degrees of freedom. We want to test at the 95% confidence interval, and so we would go out to that level of 0.05 for alpha. We would go down to 4 degrees of freedom, and we would find that the table value is 9.488. And if the observed chi-square value is bigger than this value, then those distributions that you observe are not homogeneous. Some of them are larger than they should be, some of them are smaller than they should be. And of course, you can look at the contributions to the chi-square test and see that these are not homogeneous because the $10,000 policy and the, what is it, 25? I don't even know. I changed sheets. And the $20,000 policyholders tend to cancel policies more frequently. And also the $15,000 group also cancels slightly more often than the ones that higher values. So all it's telling you is that this distribution doesn't match this distribution, and this distribution doesn't match this distribution, primarily because of one group being canceling somewhat higher than other groups. These are both below, canceling less often than you would expect. These are canceling more often than you would expect, and these are canceling about what you would expect. So this is the nature of it. Recognize that in this case, these are both canceling, these are both canceling less often. This one is canceling more often. The values don't tell you what direction the deviation is. It just tells you the magnitude of the deviation. You actually have to go back and look at the data to see whether it's a deviation upward or a deviation downward. Chi-square test of homogeneity. Questions on how it operates? Yeah.
Which ones are less than?
So if the expected value is 50, so these all have large contributions to the overall chi-square being statistically significant. So these three and this one all contribute heavily to this one. This one doesn't contribute hardly at all because it's very close to what is expected. In these cases, the number canceled is lower than the expected. In this case, it's considerably higher than the number expected. So even though they're all contributing to this chi-square statistic being bigger, 2 of them are because canceling less, 1 of them is because of canceling more.
So you look at the actual.
You have to go back and look at the actual data. Yep. Yeah.
How'd you get the 9.488?
I looked it up in the table.
Oh, okay.
So you go to the number of degrees of freedom that you have for your test, go over to the alpha level that you're testing at, and that's your critical value. And if your chi-square value that you observe is lower than that, then your data set is homogeneous. If it's higher than that, it's not homogeneous. Okay? Yeah.
This is a separate chi-square table that we need to know, or not that we need to know, but that we need to be able to interpret at least.
You need to interpret it. Yeah, sure. So if the, not T, if the chi-square that you observe is greater than the chi-square, this is sometimes called the critical value. It's the value in the table. So some people write it as chi-square crit. Some people refer to it as chi-square in the table. If the one that you observe is bigger than the one in the table, not homogeneous. If the chi-square is less than, the chi-square in the table, then you would conclude that it is homogeneous. So think about this. The more categories you have, the more differences get added up. So as you go from the bottom of the table to the top of the table to the bottom of the table, you're increasing the number of categories that you have. So the tabled value of chi-square increases, but that's mainly because you're adding up more differences. The other thing that makes differences add up in the chi-square table is those situations where you have a lot of disagreement between what you observe and what you expected. So the chi-square is significant if these differences get big. This difference is big, that difference is big, that difference is big. They're all driving the chi-square to be big, which signifies to you that they're not homogeneous. Okay? So it's always a comparison to this. If what you observe is bigger than that, they're not homogeneous. If it's smaller than that, they are homogeneous. This is just the opposite of the ordering of values in the t-table, where they were biggest at the top and smallest at the bottom, because that's a different kind of table. So, questions? So for an insurance company, they might ask themselves, why do individuals here cancel their life insurance policies less often than people who are getting bigger policies? Well, it might have to do with the fact that premiums for low value policies are lower, and as a result, they are less likely to cancel those policies. And premiums for higher value ones are higher, and so you might be more likely to cancel those policies. So, sorry, what did I say? Oh yeah, you're less likely to cancel them at lower values, probably because premiums are lower. So what a company then does with the data is up to them in terms of their decision making. The question that they have is, does it vary across categories? These are actual data from an opinion poll during the last presidential election. Once again, we only have opinion polls from the Democratic Party because the seat was not contested in the Republican Party, so we only have really Democratic polling to rely on. This is a poll that was taken in January 8th of 2008, and what they found was they surveyed 1,000 individuals. 293 of them favored Biden, 203 Sanders, 148 Warren, Buttigieg, Bloomberg, Yang, Klobuchar, Gabbard, Steyer. Some of these people you probably don't even remember any longer, and then 97% either chose somebody else or didn't make a preference. These are the observed frequencies of people expressing support for each of these candidates. How would we calculate the expected values if the question that the pollster has is there a preference? Yeah.
So I think it's what?
It's 11, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. So we have 11 candidates per categories.
Divide 1,000 by 11, get your expected value.
And so that expected value would be the same for everybody.
Right.
So the expected values would be 90.9, let's just say. The thing about the expected values, and I didn't illustrate this, I didn't call attention to it on the last one. The expected values should always sum to the same value as the number that you observe. And so we can test that by adding all of those up, and you would get 1,000. Now, one of the questions you might have for me is, do I have to carry all of the decimals out? Yes, you do, because if you round to 90.9, you're going to get this thing summing to less than 1,000. And so you need to make it such that it does sum to 1,000. So then what do? Take the observed minus the expected. You square that difference. You divide it by the expected. And you sum that up across all 11 categories. Homework for Friday. Wait. Yeah, Friday. Today's Wednesday, right? Today's Wednesday. Homework for Friday. Work this out. For these candidates, there is a chi-square table. In this case, since you have 11 candidates, you would have 10 degrees of freedom. So the chi-square critical value is 18.307. So if your chi-square statistic is bigger than this, then there is a preference. If it's lower than this, there isn't a preference. Yeah.
You just want us to give them the table and send it to you on Friday?
No, I want you to bring it into class on Friday so we can talk about it. I don't need to see it until Friday. So we have 9 minutes left. It's going to take you guys at least 9 minutes to do this. So you can sit and work on it now, and I can help you, but you can also work on it in your spare time. We're not going to probably get to talking about the results today, which is why I'm like, do this for Friday. All right, any questions?
And then the homework that you assigned on Monday is due Friday as well, right?
Yeah, that gets turned in. This is just to get us moving along in the conversation. Yeah. I still want it printed out. It's just easier for me to sit in my armchair with a sheaf of papers and read rather than like booting up a computer or iPad or something like that. Yeah. Yes, ma'am.
On Friday, I'm traveling for softball. We leave at 7:30.
Stick it under my door.
Okay.
The homework?
Yeah.
Yeah.
Where's your? Sorry. Where's your?
Down one floor in white science and right next to the horse skeleton, 142.
So
Yes.
we just do the same thing.
Yeah.
we did with-
So pull that. Well, I see it now. So it would just be the chi-square is going to be 293 minus 90.90900909 divided by 90.90900909, et cetera, et cetera.
So is it easier rather than type out the 9.09 to just do the 1,000 divided by 11?
You could do that. That's what I did. So actually, I did this in a spreadsheet simply because working with those decimals is a pain in the butt. Yep.
Yeah.
Yep. And then, so that would be it for Biden. Then you would add for that Sanders, 203 minus 90.909009 divided by 90.90909. But of course, these differences in the numerator get squared.
Oh, yeah.
So always remember this equation. You square them, then divide them, then add them all up.
And then if it's greater than
Mm-hmm.
that number,
If what you find is bigger than this number, it means that there are differences. They're not homogeneous.
yeah.
And that should be obvious to you. Clearly, people are preferring Biden over what you would expect.
Yeah.
People are preferring Sanders over what you would expect. People are preferring Warren over what you would expect. And all the rest of these, they prefer less.
Yeah.
And so all of those differences, these big differences and also these moderate differences to big differences in the other direction, those are all going to stack up to give you a really big chi-square statistic in the end, which basically tells you if the chi-square critical is smaller than the chi-square value that you observe, then there are differences between what you expected and what you observed.
If it want to be smaller,
Then there would be no preference.
oh, yeah.
So if everybody was getting around 100 people responding that they favor those people, it would be much more evenly distributed across the 11 categories. And as a result, the chi-square test would be really small. The chi-square that you calculate would be really small. You know, if everybody was down here, there's zero preference for other, whatever other is.
Yeah.
Because 97 versus 90, that's a really small difference between observed and expected. People are actively against Booker.
Uh-huh.
People are actively against Steyer. Actively against Gabbard, Klobuchar, Yang. Actively in favor of these other people because these are big differences. These are big differences, but these are big differences that indicate preference. These are big differences that are rejection.
Thank you.
Sure. So that's the other thing. Having an intuitive feel for what the test is actually trying to do is useful because it helps you in terms of interpreting what the answer is at the end.
Oh, Dr. K,
Yeah.
last question. If we do it on paper, for example,
Uh-huh.
the homework, does that, like, we just have to put the question and our answer, right? We don't have to write out the entire question. Or sorry, we just have to put our answer down, right? Like,
Yeah, just put your answer down.
right?
Yeah, yeah.
Oh, yeah.
Yeah, there's questions there. I left you space to write your answers. That's all I'm looking for.
Okay,
Yep,
perfect.
yep.
Sounds good. Thank you.
Yeah, I saw in the middle that the submission time is 5. I'm
Yeah,
assuming-
end of the day.
Oh,
Yep.
okay. Just get it to your office by that time?
Yeah, yeah. It's practice homework. You're not doing it to prepare for something on Friday.
Uh-huh.
So I could make it due at the beginning of class, but that really serves no purpose because
Yeah.
it's not preparing you for the day's activities. It's asking you to practice things that we've already been through. So for me, it's academic as to when it gets turned in. So just get it to me by the end of the day. Yep. Miss Wilson, what are you doing? Are you doing the calcs? Good. You're going to find that the chi-square test is very large. Chi-square statistic is very large. Democrats definitely had a preference.